In this video, we want to learn about partial fraction decomposition method for functions that their denominator is a product of linear factors, that some of which are repeated. Let us start by this example. X to the 2 minus x plus 1 over 2x minus 1 times by x plus 2 to the 2. When we look at the denominator of this rational function, we can see that we have 2x minus 1, which is a linear factor, times by x plus 2, which is again a linear factor, but it is raised to the power of 2. And this is new. In the previous videos, we haven't seen something like this. We had linear factors, but all the linear factors were to the power of 1. But here we have a linear factor, but its power is 2. It can be 3 or more. How we can write the partial decomposition for such rational functions? When we have something like this, we start with 2x minus 1. Similar to the normal rational functions, we put the linear factor in the denominator and we put the unknown a in the top. Then we have linear factor x plus 2, so we put x plus 2 here with the unknown in the numerator. But because this linear factor is raised to the power of 2, we have to also add this third fraction here with an unknown c in the numerator. So when we have a linear factor that is repeated, we have to put the linear factor in one fraction, and also we have to add a second fraction with power 2. What if the power was 3? If the power here was 3, then we have to add another partial fraction in the form of d over x plus 2 to the 3, and so on. So, depending to the power of linear factor, we have to add more partial fractions. Here, in this particular example, we are not looking for finding the unknowns a, b, c. So we don't want to find these coefficients. Just we want to write the form of partial fraction decomposition. Let's move to the next example. 3x to the 2 plus 5 over x to the power of 3 times x plus 4 to the power of 2 times by 5x minus 1. Note that here 5x minus 1 is to the power of 1. But x plus 4 is raised to the power of 2. So it is repeated. And attention, x to the 3 is basically x, which is a linear factor, raised to the power of 3. So it is repeated 3 times. Now that we know this, we can start writing the partial fraction decomposition for this rational function. And of course, before we start writing the partial fraction decomposition, always we check that the degree of numerator is less than the degree of denominator, which it is here. And also, if you check the previous example, here we had this example here, the degree of numerator is 2, but the degree of denominator is 3. Attention, here we have in the first bracket, we have x. In this bracket, x raised to the 2, so we have x2, and this x2 times by this x in the other bracket, it would be x to the 3. So the degree of denominator is 3, and so the degree of denominator is more than the degree of numerator, and so we don't need any line division here. But if the degree of numerator is bigger than or equal to the degree of denominator, we have to do first the line division, then we do the partial fraction decomposition. Let's back to this example here. First, for x to the 3, can you guess how many fractions we need for that? Yes, we need 3 fractions, x, x2, and x3. And of course, in the top we have a over x, b over x2, c over x to the 3. Then for the next fraction, we have x plus 4 and x plus 4 to the 2, d and e in the top. And finally for 5x minus 1, which is raised to the 1, just we have 5x minus 1, and in the top we just put f. As you can see here, we have 6 unknown coefficients, a, b, c, d, e, and f. So we have 6 unknown. And of course, finding all of these unknowns needs a lot of calculation. And usually we use softwares to find these unknowns. Finding these unknowns by hand, if you want to do it by yourself, it's not really easy. So we leave this example here and we move to the next example. In this particular example, we want to write the partial fraction decomposition, and also we are going to find the coefficients. But attention, the denominator is not factored. So first we factor the denominator before writing the partial fraction decomposition. If you look at the denominator, we can factor x to the 2 from these two terms. So first we rewrite this expression as x minus 1 all over x2 times x plus 1. Now, because of x to the 2, we put two fractions, x and x2, and in the top we put the unknowns a and b. And for x plus 1, we need just one partial fraction with an unknown on the top as c. So we have three unknowns, a, b, c, and we have to find these unknowns. The standard method for finding the unknowns is to multiply both sides of this equation. Attention, this is an equation that we have here. This expression should be equal to this expression. So this is an equation. To find a, b, and c from this equation, the first step in the standard method is to multiply left side and the right side by this denominator. When we multiply both sides of this equation, left side and the right side, by this denominator, we can get rid of all of the denominators. So we multiply left side and right side by x2 times x plus 1, and also we multiply the right side by x2 times x plus 1. When we multiply this fraction here by this, the numerator and denominator cancel each other, so what remains is x minus 1. But in the right side, when we multiply this in the first fraction, this x from denominator with 1x from numerator cancels. So what remains? 1x times by x plus 1. So we have x times x plus 1. Again, what happened here? 1x from this x2 with 1x from denominator cancelled, and 1x remains. So we have ax times x plus 1. When we multiply this in this fraction, x2 with x2 completely cancels, and then we have plus b times x plus 1. And finally, when we multiply this fraction, x plus 1 with x plus 1 cancels, and what remains? cx2. Now here we are going to multiply the brackets, the expression outside of the brackets to the brackets, and simplify. X minus 1 equals ax2 plus ax plus bx plus b plus cx2. Again, we keep the left side. Here we have ax2 and cx2. We can write it as a plus c times x2. We have ax plus bx. We can write it as a plus b times x. And at the end we have b. Now we are ready to find a, b, c by equating coefficients of the left side with corresponding coefficients in the right side. In the left side, what is coefficient of x to the 2? What is coefficient of x to the 2 here? We have no x to the 2 here. So the coefficient of x to the 2 in the left side is 0. Because we don't have any x to the 2. We just have x and minus 1. So coefficient of x to the 2 in the left side is 0. But what is coefficient of x to the 2 in the right side? Yes, it is a plus c. So a plus c should be 0. What is coefficient of x in the left side? It's 1. And so the coefficient of x in the other side, a plus b, should be also 1. And finally, what is the constant term in the left side? Negative 1 is a constant, is a number. What is the constant term in the right side? B. So b is negative 1. Now that we know the value of b, we can substitute this value in the above equation to find a. So, attention, b is negative 1. We substitute this value in the second equation, then we have a plus negative 1 is 1, so a is 2. Now that we have the value of a, we can substitute this value in the first equation, and then we have 2 plus c is 0, and so c is negative 2. So, finally, the factored form of this rational function is a is 2, so 2 over x. b is negative 1, so negative 1 over x2. And finally c is negative 2, so negative 2 over x plus 1. This is the partial fraction decomposition for this rational function. And again, why we learn this technique, this method? Because in integrating rational functions, we cannot integrate rational functions like this right away. First, we rewrite these rational functions in terms of simpler rational functions, and then we integrate these simpler functions. I hope you liked this video, and of course, please subscribe in my channel. Thank you for watching.